Okay, we're going to take a look at another electrostatics problem. The value of the electric field at a distance of 87.6 meters from a point charge is 5.9 Newton per Coulomb and is directed radially in toward the charge. What is the charge? Coulomb's constant is 8.99 times 10 to the 9th. Okay, so this is a little bit heavy in some wording, but it's stuff that we've worked with before. We have an unknown charge. We can do that in purple because it could be positive, it could be negative. We have no idea. We'll call it Q1. That's our charge. Now, this charge is generating an electric field, and they say some distance away, at some point over here, could be in any direction, but I'm just going to arbitrarily put it in this direction. At some distance away, 87.6 meters. And they say that the electric field is directed inward, radially inward, so it points back towards where the charge is. Radially means going kind of outward, but if you have radially inward, then it points all inward like this. Now, hopefully, you're already thinking of one of the important things that we need. If our electric field points inward, and electric fields always point the direction that a positive charge would go, that means a positive charge would move towards our unknown charge, which means we've already learned something important. Our unknown charge is negative. If it were positive, then the electric field lines would point outward radially. They would point away. Now, we've been given this 87.6 meters away from my unknown charge, and we have an electric field out here that the magnitude, we know the direction, it points this way, but the magnitude is 5.9 Newton per Coulomb. They want us to explain or find the charge here. Okay, well, our equation for the electric field at a given point is going to be equal to KQ1 over R squared. It's just like the force equation, Coulomb's law, except it deals only with one charge. We're finding one part of the force. We won't actually know what the complete force is until we put a particle there. But we are actually looking at what's called the field. And a field is a way of figuring out what the force would be, as best you can, without knowing what you're actually acting on. It is not the force. As we talked about, Newton's third law of motion states that all forces must be shared between two objects. If you only have one object, you cannot have a force. We can describe what the force would be like, how strong the field is at a given point that is generated by one object. And then with that information, we'd be able to then, when we know what object we put there, predict what the force will be, but only if we know the other object that we're putting there. All right. Now that we've got this, we can start filling in some information. We know that the electric field was 5.9 Newton per Coulomb. That's going to be equal to 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And we're multiplying it by this unknown charge, but we now know is actually a negative charge. That's okay, we're just going to solve for the number, but we know that it's negative from the directions. All right, and then divided by 87.6 meters quantity squared. So now it's just a little bit of algebra. I'm going to multiply both sides by 87.6 squared, and then divide by 8.9 times 10 to the 9th. Let's see what we get. So 5.9 times 87.6 squared, and then I'm going to divide that by the quantity of 8.99 times 10 raised to the negative 9th. If I have done this correctly, oops, not negative 9th, sorry. I have not done this correctly, times 87.6 squared, divided by 8.99 times 10 raised to the positive 9th. Helps if I do this correctly. I find Q1 comes up to, at least its magnitude, its value, is 5.04 times 10 to the negative 6. Now, we also know from the information that we were given about which way the field lines point, they point towards the center, that this is the value, the magnitude of the charge, you could say, but the number of the charge, we also know that it needs to be a negative. Now, we could go through and we could keep track of the electric field and do a bunch of other things, but that gets really difficult to keep all of these vectors straight. One of the things that I told you when it comes to forces and electric fields, just take the number, the value, and figure out the direction on your own. Okay, so we know that this is a negative charge because the field lines point in towards it, radially inward. So we know that it's negative, and we know that its value, the number, has to be 5.04 times 10 to the negative 6th. Now, the question asks for this to be put in terms of coulombs. So, yep. And in fact, this is what we would put in. Now, when you're actually typing this in, because the system doesn't always recognize times 10 to the negative 6th, what I'd recommend is 0 point and move this over 6 spaces. So that would be 1. We need 5 zeros. 5 zeros, and then 504. Don't forget your negative. Coulombs. It's a weird way of writing it. What I would actually prefer is for us to call this 5.04, negative 5.04 microcoulomb. But we're asking for an answer in coulombs. In the online system, you can put it in this way, and it should accept that as an answer.